Okay, hello, I'm Boyd, and welcome to Introducing Scenic. The subtitle for this is, What the heck has Boyd been doing for the last year? So last year at ElixirConf, I got to give a preview of some things that I was working on, and it actually kind of came about 2 years ago at ElixirConf in 2016, and I gave a presentation talking about why I fell in love with the language. And at the end of the talk, I kind of mentioned, but there's some things that are missing. They just feel like they're missing in the ecosystem. And to me, the really big one was a native UI package that's written in Elixir for Elixir in the Erlang ecosystem. It just felt like it was missing. And about 3 months after that, I was sitting at home and complaining about this, and I went, oh, nuts, I'm going to have to do it. So I started writing code, and it's bigger than maybe you expected it was going to be. All right, it's been a lot of work. And I see some of the guys from the Seattle Elixir meetup community, and they've been following along with this month to month as I come in, and they're probably sick of hearing it by now, but no, okay. All right, so I got a lot I want to talk about. This ended up being a pretty big project, so I'm going to kind of dive into it. We're going to start with what were the goals that I set out to do the project. I really believe that anytime you start writing code, you need to step back and ask yourself, well, why am I doing this? What are the things I'm trying to accomplish? And you do that before you actually start to write. It doesn't mean you're going to hit all your goals, but it's good to have them in mind. So I want to share some of those, and I've got more of these goals written out in the documentation. So the first is small, fast, simple. We've all heard of Moore's Law, and for a long time in the world of computing, we just got used to bigger, bigger, bigger computers, and it kind of feels like Moore's Law has stopped. It has not. It is running apace. It continues as it ever has been. But instead of making bigger chips with more transistors that have more power, they're using Moore's Law to make smaller chips that have the same number of transistors. They're just less expensive, and they use less energy. Right? So it's a different mindset. We have to actually go back to the way it used to be and think about how do we write software that is power efficient, because we're not getting more transistors. We're just getting cheaper chips. And especially when you think about the world of IoT and connected devices, the way those devices get chosen is the manufacturer starts by saying, OK, what's the job this device is going to do? Now, what's the absolute cheapest piece of hardware I can purchase that will still do it? Right? That's the world of IoT, and the world we have to live in as we think about software for it. So to me, when you're building a device that's going to be in the field, starting by putting 150 megabytes worth of browser on the device is a non-starter. Right? I want to target something much smaller than that. It has to be robust. I worked on game consoles for a long time, and it's effectively a really big IoT device, right? A heavily overpowered IoT device, but it's got the same set of issues. You don't necessarily have a user who's going to go in and open up a command line and figure out things that are broken, right? And likewise, think about IoT now. I've got a device that's up on a telephone pole, might be 10 miles away. If you have to roll a truck to that device, you've failed. So we have to have software that knows how to self-heal, that knows how to restart itself. And that sounds like OTP. Right? There's these high availability techniques from the world of servers that really want to come over to the world of the client and to make client software that handles failures, knows how to reboot itself, knows how to keep going, and is desperately going to try to keep going in the face of adversity. It needs to be remotable. These devices, by definition, are not where you are. Right? If they're in the field, they've been deployed, they're doing a job, and you don't want to send somebody out there. I wanted it to be approachable. So this is not HTML. I got a couple of non-goals. It's not a browser. It's not 3D. It's not immediate mode graphics. And if you know what that is, that's OK. It's a retained mode graphics system, and more like HTML is. But approachable. If you know HTML, I wanted to have concepts that would seem familiar. You'll come into this, and yes, the syntax is completely different because it has nothing to do with HTML, but the high-level concepts will feel familiar, and we'll go through those as I'm talking. Secure. The first thing you do with security is you keep it really simple. I don't want to have 150 megabytes worth of code, including JavaScript and interpreters and all this complexity that I don't understand. You start by stripping all that back and give me a machine that does as little as it can do, and it still gets the job done. I don't want any open ports. It can talk to a server, but I don't want to sit there receiving anything. So that means I can't SSH into it. And I want to have good static asset hashing. A lesson learned the hard way. If you have an image on a drive in a connected device, and you load that image, and you don't check the hash of the image at the time that you load it, somebody will manipulate the metadata in that image, causing you to buffer overrun, and now you're booting into some other piece of code that you weren't expecting. I've seen that happen. Right, so you have to hash all your static assets. And then much more. I'm going to say much more about this at a later date. OK, now the last two goals are really flip sides of the same coin, and to me they're really important. And the first one can be summarized as never trust a device if you don't know where it keeps its brain. So today we buy these devices, like I did this, right? I bought a router off of Kickstarter, and the selling point of the router was you could go to this web service that they had, and you could configure the thing. So if I'm off traveling and someone at home is having trouble with it, I could log into the router, and I could figure something out. And it worked really well for about 3 months until the company folded and the server went down, and then it didn't work at all. Right? The brain for the router was on the server. It wasn't in the router. Now that's, it wasn't very expensive. It didn't hurt me very much. But now let's say you've invested $1 million in a highly specialized truck, and you're making your living off of this thing. Maybe it's got natural gas equipment, it's got sensors, it's got all this stuff on the truck. 3 years later, the company you bought the truck from has been acquired, and their direction has been shifted in a different way. Does your truck work? Do you still have an income? Well, I don't know. Where's the brain? Is the brain on the truck? Or was the truck making RESTful calls up to a server all the time in order to collect its information on how it's supposed to run? And if that server goes away, what happens to this capital asset that you've invested your life savings into? I don't know. The brain needs to be on the truck. The server still has a role to play, a critical set of roles, including authorization and all kinds of other stuff. But I want those devices to continue to work even if they can't talk to the server. Now so where's this brain? The flip side is from the company's point of view. If you're making the truck, let's say in year one you've got 5 different versions of the truck, and they're all talking to your server, and you've got code on your server that's talking to these things, and it's great. It works really well. And I see this a lot right now. 10 years from now, you've had success. Every year you've introduced 10 new versions of your truck. Maybe you've got 100, maybe you've got 200 versions of the thing that you're servicing from your server. Your dev team is now in matrix hell. Instead of working on the new truck for this year, the one that people are going to pay you for, they're spending all their time making sure that changes to the server don't break the fleet that's already driving down the street. Right? You can't move forward anymore because you put the brain on the server, and it gets ever bigger and ever more complicated. OK, so those were things in my head as I was designing. So now a really brief overview of the major pieces of Scenic, and then the rest of it's going to be demos. So Scenic is a 3-layer system. The top layer is the scene layer, and this is where people will spend almost all of their time writing code. You create scenes. A scene is like a web page in the sense that it is a screen of UI. A scene has a graph. The graph is sort of like the DOM. It's a hierarchical layout of things that can get drawn. The graph has primitives, a single thing that can be drawn, and you can apply styles and transforms, and that all sounds kind of familiar. The viewport layer sits between the scene layer and the drivers at the bottom. The viewports layer job is to collect graphs coming from the scene, prepare them for use by the drivers, and send them down below. It also collects input coming up from the drivers and hands them up to the scenes, which was easy to say, and I swear that was like a quarter, maybe a third of the whole time was trying to figure out those two flows. That was incredibly difficult. And then the driver layer at the bottom is pieces of code that are isolated, and they know about the specific hardware they're running on. Drivers know how to take a graph and render it. They have no idea what scene it came from, and they don't care. Right, so very isolated down at the bottom. So likewise, scenes on the top have no idea what drivers have been installed, and they don't care. So drivers render things out to the screen, and they collect raw user input, which hands back up to the viewport. So briefly, a scene, analogous to a web page, it is a gen server process. This is where you hold your business logic state. You have a graph. You react to events. There's two kinds of events. If user input happens, you create a handle input handler. And if another scene is sending you a message, then you do a filter event, and we'll go through that. Viewports, the intermediate management layer, they handle graphs going down, input coming up. Driver layer catches the input, and you can mix and match these drivers to achieve different purposes. And we'll see that in action. And then finally, I'm building a service to go with all of this. You know, it's nice to be able to make a device that has a UI that you can use, that you can mess around with all the graphics, but what's the point if you can't then remote into it from a different location? So I'm building a service that will allow you to register these devices. You can go onto it online, you can connect to them, you can use them remotely. It will offer services like audit trails. Hey, this valve exploded and the device is gone, and we want to know what happened. Well, you can't do forensic analysis on the device because it melted. Let's go back to the audit trails and replay the UI as the operator was using it. That kind of thing. Working on debugging services, logging in the cloud, all kinds of things that we have in mind. And if you go to Crichton.com, which is the company I'm forming, it right now says it's a coming soon page. That will change soon. OK, let's see what this is actually all about. So we're going to start with a simple scene. And I'll make it bigger. OK, so this is a very simple scene. And at the top, you see use scenic.scene. That is part of what it does is it calls use gen server. So that creates a gen server, which is your scene. It adds a bunch of machinery so it can talk to the viewport. The main thing you see at the top is the compilation of the graph, graph.build. And I'm doing that at compile time. You don't have to do it at compile time. You could do it at runtime. But first thing I want everyone to think about is these are small devices. What code really needs to run at runtime, and what can you get done in advance? Right? You know, when you bring a web page down onto the client and you think about how many milliseconds until you see the first thing rendered on the screen, a lot of that time is parsing the HTML and figure out what to do with it. I want to do that at compile time. Right? So this will generate a term that gets stored in the binary, and there's no work at the time that you load the scene. It's just done, and it runs, and it uses less power, and your battery works better. So this particular scene is very simple. It's got one text item, and then you see how I'm piping? You build the graph, and then you use pipes to continually add things to it. So I add the text, and then I'll add a circle. And then in the init function, I'm going to call just one call, and that's pushGraph. PushGraph gets added to your scene, and that's what tells the viewport this graph is now ready to be displayed. When you push it to the viewport, it does its magic, prepares it, and sends it down to the drivers. All right, so let's see what that looks like. So I'll do. You can do either ix-s mix, that works, or if you don't want to run with the ix running, it's mix scenic.run. And there it is. We have a window. And it's that simple, right? That's the goal, to have it be approachable. It feels a little bit like writing a web page. You build scenes, you add a graph. Let's look at something more complicated. I guess I'm going to have to make each one of these bigger. OK, so this one of the first things you'll do when you're playing with it is you'll see I've created a mix. There's an archive that you install, and there's a generator for a new project. So you go Scenic, new, and then you name the thing. And this is the app that it will create for you. I really wanted to have a good example you could look at and see how to build something that's more complicated. So this scene is one of the first interesting scenes that you encounter, and it's pretending to be it's a scene that is reading data from a simulated temperature sensor. It shows that data on the screen, and then it throws a couple buttons in place where you could then do stuff. This graph is built here, so I'll add some text. You see it's an empty string. That's where the temperature is going to go. And then there's a group. A group is like a div, right? So you put stuff in the group, and then you can add styles to the group or to the things in it. Inside the group is 3 different buttons. And then down here at the bottom, I'm going to add a navbar and some notes. Now the button, the navbar, and the notes are what I'm calling components. A component is just a scene that has a little extra sugar on it so you can call it from another scene. All right, now the idea here is that if you've built UI like a button, which by the way, everything is from scratch. I had to worry about the angle on the little rounded corners on the buttons, and when you press the button, does it change colors? That logic is incorporated into the button scene. You don't want to redo that every time you add a button. So that spins up a second gen server, which is the button. Your scene is over here, and there's a relationship between them that's maintained by the viewport. Right? And that lifecycle management of the relationship between those scenes is all kind of managed for you. So when we start this one, actually the first thing that's going to happen is it's going to play a splash screen. This is a splash screen. It's a very simple graph. It's got a single rectangle, and in the rectangle it's going to paint a bitmap, except it's going to start with an alpha channel of 0, so it's going to be transparent. And then it's the init function here, right here, starts a timer, which is going to cause a little animation to happen, and it's going to modify the graph, changing the alpha channel so the parrot will come in. All right, let's see it go. And this time, let's do it in the in IEX. Okay, there's the splash screen, and there's the scene with the temperature sensor. Now you see the temperature data is changing. It's because there's I wrote a little gen server that's got a little, it's just doing a little cyclic variation on a temperature, and it's publishing it to a pub/sub temperature sensor, which is also in there, to a pub/sub sensor cache, which the scene is subscribed to. As the data comes in, it's collecting events. It reacts to those events by changing the text in the field that shows the temperature. So we can look at that. So down here, I got to look at the Scenic, at the sensor scene. Let's see. So I'm doing a handle info, just like you do with any message. And this is coming from the sensor, and this is the magic. I take the graph, and I pass it into graph modify. Just like you would in HTML, you can put IDs on things. So this right here, that string has an ID of temperature, which is an atom. So I say I want to modify the graph. That's the atom I want to modify, and then I'm going to pass in some new text. And every time the temperature sensor thinks it's got a new value, it sends me that message. I catch it in handle info, I modify the graph, and then I push it to the viewports again with push graph. And this is a pattern that just repeats all over the place. Now, this has some other more interesting graphs, some other more interesting scenes. Another scene in the same one is the primitive scene. We'll look at that in a sec. This is a graph that shows all the different primitives that you can draw on the screen. There's only like 2 handfuls of them. And it turns out that's all you need to draw just about anything. You don't need much more than just a small set of primitives. But before we get there, let's look at this component here. The navbar that we saw at the top, let's look at it again. This gray thing at the top that's got a clock and it's got a drop down. See the drop down? That is a component, which is right here. A component says use Scenic component. This is just like making a scene. You create a graph, which is here. You initialize some things in it. And when you push that graph, the system picks it up, starts up the other components like buttons or whatever that you requested. And then this component, when it gets called by the first one that we saw, which is the temperature sensor, you end up with a cascading set of processes that get created. And the whole point is to isolate the logic so it's reusable. I didn't want to have to rewrite the nav bar for every different scene. I wrote it once, and now every scene that wants can just slide it in, and it works. So before we look at the observer graph of the supervision tree, let's see what it actually looks like. So when I go here, that triggers the drop-down that was in that nav bar component. I'll pick primitives, and it switches the scene. And those are the basic set of primitives that you can draw. Each one has got a stroke. It can be filled. The red squiggly thing is actually an arbitrary path that you can connect with line 2, Bezier 2. You can do it one way, and you'll fill it. Do it the other way, and you'll cut holes in it, all that. You can see you can bring static images in. It's got text. It's actually pretty much what you need. And every single component, including the drop-down, including the buttons, including everything, is built out of these primitives. All right. Actually, before we go to Observer, let's look at this one. This graph, this scene is the component scene, and I wanted to demonstrate all the basic components that are pre-built into Scenic. So this graph, you'll see I put some text in, and then I've got a bunch of buttons, and I've got some sliders. And let's just go take a look at what that looks like. It would be this one. If it looks a little bootstrap-ish, that's sort of on purpose, right? That can be changed. I mean, you can pass a map of colors in, and you can pick whatever colors you want for the buttons. But again, I wanted it to be familiar, right? Not completely foreign-looking. So what happens now is each of these controls has spun up a separate process that's being managed in a supervision tree. So if any of these crash, they just restart. And the way they communicate back to the component scene is when you do stuff with the control, it generates a message, which it passes to your process, and you catch it. And so in this case, here where it says event received, it's going to catch all the events, inspect them, and render the text of that event out. So if I start clicking buttons, you can see what happened. If I start using the slider, you see the radio group works. There's a drop-down. I can check a checkbox. Those are the things you expect. Interesting challenge, when you go back to the basics, you realize that we take these things for granted. I haven't thought about what does it mean to write a control in a long time. And I had to spend time agonizing over what should the radius of the radio button be? And what is the color of the little thing that says it's been checked? And how do you draw a text control? And what happens when you type in too much text and it goes over, right? Can you have a scissor region so you say limit it to that? But those are all built in, and if you look in the Scenic source code, you'll see exactly how I did all of that. Now let's bring up Observer. All right. Okay. I learned a lot about supervision trees while doing this. Let's look at the bottom row. That's the interesting bit for now. It starts on the left where it says Scenic, and there it starts a set of tables. There's a table process. There's some caches for static images. And there's that anonymous row. That's interesting. This anonymous row that goes to the middle, the bottom one says main viewport. The viewport is the thing that manages the window. If you want two windows showing, you need two viewports, right? So one viewport, one window. On an IoT device, you have one viewport because you got one screen. At the top, you see there's a little branch that one of those says GLFW. Those are the drivers that the viewport is associated with, and the middle is your scene. And you see those boatload of processes on the right? Those are all the buttons and the sliders and the things that your scene created when you requested it. So if we leave this open, I'm really happy that these monitors are this good, because that means if I come over here, and let's move it out of the way, and we switch back to primitives, it switched scenes. The viewport mechanism realized, oh, I've got a new root graph. It scans that, sees that all the different sub-scenes, the components that it references, changed. It spins down the ones that aren't there anymore, and it spins up the new ones that it needs. So it's cleaning up after itself, and there's not a lot you have to do to think about it, but it's dynamically building a supervision tree that Erlang knows how to handle restarts on. And let's look at that. So here we are, we're on the components page. Big thing came up. I'm going to add a bunch of states. So let's move the slider. We'll type in some stuff here. Move this down. Put the radio on A. Then I'm going to hit this crash button, which is fun to write a piece of software that says crash. That's going to get caught in this filter event function. And all it does is raise. It's just going to raise an error. It's going to raise an unhandled exception. That will crash the scene process. I really don't care how it crashed. I just wanted something really simple that wouldn't throw warnings when I do the compiler. So I'm going to raise an error. That will crash a scene. And then normally all sorts of horrible things would happen. But because we're on OTP, I can simply, let's put an observer again in the background. And if you look at any of these numbers, if you want to see it's actually doing it. So I'm going to hit crash, and boom. All right, it crashed. It restarted. Everything is still usable. This was like a moment when I'm building this thing, and the first time I did this, and I crashed the scene, and it came back like that. And half the time, it doesn't even blink, and it's usable. You can tell you lost a little state. It's one of those moments when you get shivers, right? And as I've shown it to people who have done software their whole careers, and I get to this part, and then I start crashing it, and they go, oh. That is really neat. And I get to this point where I'm like, oh my gosh, OTP really needs to be our client stack. I mean, this is what it's good at. And, okay, so we've got a couple things going on here. I will crash this one. Kill this process, blam. That was the radio group that just crashed. I didn't lose a state on the slider. And that's when you realize what OTP is really giving you is it gives you a way to limit the blast radius of a bug, right? A portion of my tree died, it rebooted, the rest of it's still running. Right? The sensor process that's doing that simulated temperature sensor has no idea I've done any crashing here. It's still going. And that's like, oh, okay, I kind of like that. Yeah. Oh, and you can see in the command line, those are all the error things that went flying by. So let's do another one. So I want to bring this back up because I want to have it kind of fresh. And now I'm going to open a second one. So what this one's going to do is this one is going to connect to a Phoenix server that I have running over here. And this, let me make it bigger because you can't see anything. This is going to open another Scenic app. But this one, I've taught about the service I'm writing. So it's going to go connect to the service, and it's going to request a remote of the first one that we were just looking at. So let's make this a little smaller. Boop, boop. There we go. So what we're looking at is the device on the right is the real device. That's where the brain is. That's the only brain. It has two drivers associated with it. The first driver collects the graphs that are coming down from the scenes, renders them to a window, and you see it on the screen. The second driver also collects the graphs that have been sent down by the scenes, serializes them, puts them on the wire, sends them up to the server, which reflects them back down to the client that's listening, which then deserializes them, and then, hey, hands it to its viewport, which sends it down to its driver. I know, it's like, this took a little while to figure out, but it actually works really well. So now, if I've got the operator over here on this side, and they're using the device, right? You can see what's going on. On the right-hand side, thank you. But now flip it around. The scenario is it's a cement truck. You've got a load of cement. You've got to worry about how much water you're adding. You've got to worry about the speed you're turning the drum. You've got to worry about the temperature. The driver's unexpectedly stuck in traffic. If it takes too long, if you don't change those parameters, you're going to lose the load. The driver's got his hands on the wheel and can't really be looking at the screen. So the engineer at the cement factory wants to remote into the truck and change the parameters. That's the other window, right? The brain is on the truck, right? You don't have to have the truck software running on your remote machine. I've just connected to the truck over here, and now I start using it from the engineering side. Now, in this case, the one on the right is collecting the user input, but it doesn't have a brain. So it collects the user input, it serializes it, passes it back to the server. The server says, oh, well, do you have write permissions? Checks. Yes, you do have write permission. Sends that input back down to the original device. That driver then says, oh, look, I've gotten some user input, and hands it up to the viewport. So the scene running on the truck doesn't care if the input came from a local touchscreen or from the remote one. It doesn't care. Let's see. So let's make it harder. Let's stop the service. OK, so first thing we can see, and I'm going to have it covering it up. First thing I can see over here is that this bar on the top, see how there's a little bar on the top of the remote one? That's actually its own scene. It's a component. And that component is listening to presence on the original device. So, and it can tell that the socket went down, so the server went away. I can see I'm disconnected from the server, and I have no idea what state the actual device is in. So you're going to start getting drift. This is going to start to change. Oh, I didn't talk about that scene. That's important. So let's put it over here so we can see it's different. And then this guy comes back up. And as soon as the server comes back online, they both synchronize, and it starts working again. Likewise, the client device loses power. Blam, it's gone. The device over here on the right, the one that's listening, it can see that the server's still online, but that the remote device is now offline. Oh, OK, that's what presence is good for, right? So let's bring this one back. That was over here. No, that wasn't this one. It was this one. All right. That feels pretty good. All right, there was one more scene I really wanted to show so that you could kind of get the feel of it, and that's this one, transforms. There is one way that it is very different from HTML, and that is how it gets laid out. In HTML, you do not know the size of the client. It could be a little screen, it could be a big screen, it could be a window, it could be a phone. You don't know. That's not my scenario. In my scenario, my first scenario, the one I really care about, is it's a fixed device, which, now that I'm thinking about it, I should plug in. Let's let this get started while I'm talking. So it's a fixed device. It's got a screen, and you know how big the screen is, and it's not going to change. Right? So you don't need the auto layout stuff. It's nice, and we're used to it, but you don't actually need it. So instead, what I decided to do was I'm going to build layouts the way you do it in a game. And the way you do it in a game is with matrices. And that sounds scary, but it's really not. Let me get this plugged in. OK. So, and it lets you do some really cool things. The group that's down in the middle, that's a group. And there's a bunch of sliders up on the top. What the heck? Let's look at the source for it. OK, so here's the graph. This section here, those are those sliders, and they're numeric sliders. They go from, this one goes from 0 to 500. This one goes from negative 1.5 to positive 1.5. Then here's this inner group, which has got the text and a quad and another slider in it. And as you change those first sliders, what they do is they catch that the value changed. It modifies the graph. and it starts adding matrices to it. Now, you don't have to know how to build a 4x4 matrix in order to do this. You say translate this far to the right, this far down. So you say translate, and then here's 2 values. It's a point, because this is 2D, right? Or let's see, you could do a scale one. I'm going to put in a 1.2 or a 2.0. I'm going to scale it bigger or smaller. Or what the heck, this is a matrix. That means I can make it rotate. So let's look at that. Now, what's cool is that when I click on the screen on that angled slider, what the driver doesn't know anything about the viewports, right? So the driver says, hey, a point happened right here. And the viewport then says, thank you. I'm going to go scan those graphs, but I know what those matrices that have been applied are. And the neat thing is when you take a stack of matrices, because see the sliders on the top added matrices to the group, this slider down here in the middle will put a matrix on the quad. They multiply together. And when you multiply the bunch of matrices together, you get a final matrix, which gives you a set of vectors that you can transform things by. Sounds complicated, but the reality is, I click on it, the viewport figures out the inverse matrix of the final object, uses that to transform the point into local coordinate space. The slider thinks it's horizontal, it thinks it's at 0, 0, and it thinks it's at 1.0 scaling. So what happens now, when I click here, is it just works. And that works across the board. You can have lots and lots and lots of matrices. It can go really deep. And this isn't new math or anything. This is how video games do everything, right? This is what GPUs are really good at, is you build everything in a game with matrices stacked upon matrices, stacked upon matrices. And I thought, well, if I'm not trying to solve the general auto layout because I don't know what size it is, then this is a much better way to do it, because now I can do the inverse matrix and have interesting transforms almost for free. Okay. Now, what do I have here? This is a Nerves device. It's running Scenic. My first scene that I wrote was I put touchscreen on it, and I collect it, and I wanted to know that was I mapping it correctly to the screen? This is an older build, by the way, so it doesn't look quite as pretty as some of the other stuff, but it's got a little dashboard. There it is. And I can crash it, and it just keeps working. Okay. So let's go back. I've got a deck. Let's go back to the deck. Where am I at? So I'm putting the Apache 2 license on it. It's going to be open very soon. I've waited until it was generally stable. When you start a project like this, you got a bunch of questions. You don't quite know your designs. You got your vision, but it's not going to be right. And it took a while to gestate. So I had to do this in a way where I could make broad, sweeping breaking changes and not screw up a lot of other projects. It's been a year since the last time I talked about it. I think it's pretty stable now. It's been at least 2 days since I made a breaking change. But it was a really minor one. So I'm feeling pretty good about the overall status of it. There are things that still need to be done. The service isn't ready yet. It's coming along really quickly. But that's now the focus, my focus, now that the Scenic client is in stable condition. Nerves isn't quite ready yet. Turns out building the graphic driver for Nerves is slightly different than building it for a windowed machine. But I've actually got really good progress happening on it. There's a lot of components. One of the ways I hope the community gets engaged as you're thinking about this is those buttons. The clock that you saw was a component. I want to see packages of components that other people can go and reuse. And like the clock in particular, when you get to it, you'll see I've already broken that out into its own separate package, partly because not every Scenic app needs a clock, and partly because I really wanted to demonstrate, no, this is how you roll a component out into a separate package. And then, yeah, sorry, really spotty documentation. Focus more on the guides, all that stuff. It needs a little work. And then Crichton is the new company, and it'll be hosting the service. And I'm hoping to be able to serve lots of UI over the internet. But that's not really the end. It's the end of the slides. It's not the end of what I want to do. So let's... Oh, it didn't do it. Why isn't it doing it? No, all right, I'm making it private. Yeah, it's public now. Yay. Okay, so to answer that question, yes, it just went public. As I was walking into here, it got published up to Hex. So go for it. Right, go to Scenic. There's a good, read the Getting Started guide first and the overview. The Getting Started guide tells you exactly what you need to install. You do need to install a couple of components that the graphics driver needs or it's not going to draw, so please follow those instructions. The graphics driver currently works and is tested on the Mac and on Ubuntu. In theory, it works on Windows, but I haven't gotten myself to do it yet. If anyone wants to try on FreeBSD, that would be fun. And really, I haven't tried on any of the other flavors of Linux, because once I got it running on Ubuntu, I was going to demo that, but I didn't set it up. It literally looks exactly the same. You open the window on Ubuntu, it's the exact same app, and it looks exactly the same, because there's no dependencies. The only dependency is on Erlang and OpenGL. That's it. OK. Anyway, yeah, this has been a long time in the making. Thank you for listening to it, and I'll be around answering questions or whatever. OK.